You should be able to see it. Now I should be able to see it. Should be all good here. If not, obviously, just let me know. So we're going to talk about fuzzing Nomad with Nomad today. And my name is Kent Gruber. I'm a product security engineer at HashiCorp, and I love HashiCorp products, and I love security. And so hopefully we will dive in some really fun stuff today that kind of work in those realms. So I only got 30 minutes. I have a lot of content I want to cover, and hopefully I can get perfect on time. So let's get into it. And it's going to be broken down into 3 sections to try to digest it. We're going to start with fuzzing, a small introduction to fuzzing Golang. Architecture, what a fuzzing stack could look like with Nomad, and then we're going to talk about some observability, how to monitor fuzzing workloads. So let's get started with a small introduction to fuzzing Golang, which I think kind of begs like a small introduction to fuzzing. So we can kind of see. Let's start with this. Fuzzing is effectively, in short, a form of randomized input testing, semi-randomized. It's a software testing technique that provides invalid or unexpected input into a program or a function of a program. And then this program is monitored, looking for behaviors such as that the program is crashing, taking too long to execute, which could be indicative of certain problems. And this is a really good security testing technique to explore the problem space that you might not get from your traditional tests. And this is just another kind of form of tests that you can kind of think about it in that way, but with these unexpected inputs that you might not think about if you're manually writing these things. So to get kind of an idea what like this like workflow of fuzzing looks like, we can look at this kind of like closed loop system. At the bottom here, we have these inputs, and then they're mutated. These inputs could be from a sample directory of inputs. So for example, if we were fuzzing a package or a program that dealt with images, or we would have, a directory content with images. If we were fuzzing something that was doing with like, Word documents for some random reason, we have Word documents in there, like these example valid inputs that then the fuzzer can mutate, put it into the program or the function, and then if it's a coverage guided fuzzer, it will either monitor or instrument the program or the code to be able to understand what lines of code effectively are being executed for any given input. And then some behavior happens, right? A crash, maybe nothing, like normal stuff happens, or it took too long to execute, these sort of things. And this is sort of the general fuzzing workflow. And we're going to look at this fuzzing kind of problem in the lens of Golang, because at HashiCorp, we love Go. Many of our products and services are written in this language. And so from a product security engineer perspective, it becomes a really good language, obviously, or hopefully, obviously, to spend and invest time into doing security testing with. And from that perspective, Go Fuzz is arguably the de facto tool for fuzzing Golang. It's found copious amounts of bugs in the Go standard library and infamous packages, including our own. It uses similar strategies to AFL, a popular fuzzer from the C programming language of C family programming languages, and provides tooling to create hopefully repeatable coverage-guided fuzzing harnesses. And there's a really important note, especially now. GoFuzz for the longest time was like the de facto tool, but that might not be the case for long. A design draft by Katie Hockman is starting to work out what it would be like to finally make fuzzing a first-class feature of the language, which would live alongside your normal tests or benchmarks in Go. It would be another way you could run tests and have like a fuzz flag, if I remember the design draft correctly. And you can actually go take a look at like what's actually being implemented, this design draft sort of in action, if you will, at the dev.fuzz branch in Golang on GitHub. Super exciting stuff. And I'm looking forward to this finally being available as a first-class feature, even if only in beta potentially to begin with. But really exciting movement in the Go community. But until then, let's focus on GoFuzz. And if we're talking about GoFuzz, we're really going to talk about this anatomy of a fuzz, if you will. The base function harness used by the GoFuzz package. This is function that you implement that the GoFuzz runtime will run, and then we'll kind of break this down. So this function, we'll call it fuzz, and it will always start with that prefix fuzz. And then the data, which is actually a slice of bytes. So those file inputs are given and mutated by the GoFuzz program. So that data, that slice of bytes, is provided by the main sort of GoFuzz runner. And then you can return an integer. So then you do something with that logic inside of this function, take that slice of bytes and do something with it, which I'll show in a second. And then an integer that can actually be a sort of knob to help steer the fuzzer in the right direction. So returning 1 if the fuzzer should increase priority of an input, returning -1 if it should ignore any new coverage that it found, and so it won't add it as an example to the corpus, returning 0 for anything else. And so just kind of getting an idea of like what's required to implement these fuzzing functions. And we take just like a little higher level step back at it. If we remember the closed loop system from before, we have the corpus, those inputs, potentially starting, if we don't have any inputs, GoFuzz will just start sending random data through the function. And then GoFuzz in this second step here, which will actually manage running and executing this function many, many times and mutating that input, and also analyzing the coverage that's being returned by the program. And so you don't have to worry about that coverage guided kind of nature of the fuzzer. That's part of the tooling itself. And the fuzz function, gets that slice of bytes and that data, and then you do something with it in your fuzzing logic. And you return an integer, and the system, continues, circle of life sort of thing. Really, that's how that system ends up working. And then we have a full example here of like, so how do I actually use this? So this would be a full, very simple example of getting started with GoFuzz. We start with a build tag at the top of our program. And this is just a little key to the Go compile tooling to basically only use this when we're using GoFuzz tooling. So if this was living alongside of, let's say, our production code base, this wouldn't be included in our release builds because the build tag would be able to prevent that from being included. And then we have a package in Go. Everything's a package, so we'll just start with a package. And then we import some packages. In this case, we're going to import a bytes package, which is we're going to use as a helper. And then the actual target that we're looking to fuzz here, which is the image/PNG package. And we can see that fuzz function that we were talking about earlier here, where it takes in, it uses the slice of bytes. It first converts it into the proper type, which is a key point here. Obviously, a slice of bytes isn't the only type that might be interesting to fuzz, or it might not be the only argument. But what we can do is we can transform the slice of bytes effectively into any type that we like. So in this case, it's really, really simple to turn it into an IO reader. And there are other packages, in fact, literally named GoFuzz, that are for turning these slice of bytes into the proper type. So for example, taking a slice of bytes and turning it into a struct, or taking a slice of bytes and turning it into a float, whatever, what have you. These things can be transformed very simply, roughly very simply, into the proper type for the functions we're looking to target. So in this case, that png.code is looking for an IO reader, and it's transformed using the bytes package. In this case, we're just returning 0 to just kind of do like a flat line, nothing's prioritized. And this is just a very simple kind of way to get started, which kind of leads me to a very important point here, where there's actually kind of an art here to build out these fuzzing functions, and you can kind of shoot yourself in the foot very, very easily here. And so moreover, we may want to do other functions in here. We might want to both decode and encode the input, because things that may not go wrong during decoding of input may go wrong during encoding input. And we have to be very kind of careful about how we're building out these things, because we don't want to be wasting CPU cycles effectively at the end of the day. But just now we have an example. How do we use this tooling? This GoFuzz tooling sounds really nice. How do I build this thing with it? So we're going to install 2 command line tools here. We have a GoFuzz, which is going to be in charge of running the thing, and then GoFuzz build, which is going to actually build the thing, compile the actual harness into a runnable program for GoFuzz to run. So this workflow is very much like this, where I run GoFuzz build. In this case, I'm assuming Go modules. So I'm passing in this Go module name. This is an example to understand the workflow. It's very similar to a regular Go build command or like a Docker build command. But in this case, I'm passing in a Go package name. And then to understand how to build like a corpus directory of example inputs for this fuzzer, making a working directory with makedir there, and then just copying some samples, just like an idea of how this workflow looks like. And then running, manually, we're going to run GoFuzz, and we can pass in. That GoFuzz build is going to build out a zip directory, which is going to contain our harness, potentially multiple harnesses, and then we can also pass in a working directory, which remember contains our corpus. And this will just print out a bunch of logs to standard error containing a timestamp, the number of workers, which is the number of CPUs that were given to this fuzzer. By default, it'll look at the number of CPUs available on your system, and it'll default to the max. And so let's say at a 4-core CPU, it'll use 4 workers here. And you can limit it using the prox flag in GoFuzz. just as a kind of a side note there. And then you'll get some other information that's kind of important to understand how your fuzzer is doing. The corpus size, the number of files that maybe you started with are now being added over time. The number of crashers, a really important little thing to keep track of, because we're trying to crash a program here. So we want to see that number hopefully go up, maybe not too much though. And then restarts, and then just some other interesting stuff that we're going to dive into a little bit later in observability here. But just trying to get an idea of GoFuzz. When it does find crashers, it'll populate this crashers subdirectory from the workdir that will contain a hash, a hash of the actual crash input as the prefix, and then it have 3 files per crash. So just the actual raw input, the quoted version of the input, which could be useful for adding to your tests to actually fix your problems later, and then the output, which is basically the panic or the stack trace that where we can then start figuring out where the problem actually is, and then start working from there. And so that's just where the actual results live. And so this brings up a ton of challenges, a ton of questions, and kind of like leads to why running my laptop might not be a great idea. Fuzzing is very CPU intensive, especially by default, where it uses the max number of CPUs, and it will spike those like 100%. Then it's very disk intensive if we're writing a bunch or reading a bunch from our corpus directory. And so maybe especially on SSDs, we might be causing a bunch of thrashing for not a good reason, which can potentially add a bottleneck even. And then scale, like where I'm only going to be able to run a subset of fuzzers reasonably on my laptop at any one time. All sorts of things. And then we get obviously into some questions where like, how do I know if my fuzzer is actually making good progress, or how long do I even run a fuzzer for? And like the sad question, but it's not a sad question. The sad answer really is it depends. And we're going to dive into that a little bit later. So we got some challenges. We don't want to just run on our laptop. We have some questions. We want to figure out like if these fuzzers are doing good stuff. We probably want to like do little tweaks and like compare them over time, which we're going to get into observability later. But we're going to look into an architecture where like a fuzzing stack that has these challenges, like what it could look like, and solving some of those problems with Nomad. So the full stack really is a bunch of pieces, and these are kind of the core pieces I'm going to focus on in this architecture section. We're going to look at Terraform, how I used it to manage and deploy resources required in the stack. Nomad, the real the subject of the talk, if you will, orchestrate the tasks across variable compute resources, and I use Console to enable service discovery and secure connectivity between the tasks running in my cluster. I use Google Cloud in this case to deploy VMs on and other resources, and then Grafana to visualize the metrics that I have out of my Prometheus instance. And Grafana and Prometheus, I'm going to be running in Nomad. I'm going to show exactly how I set those up. And these are not even all the pieces. Like there's so many pieces that like make up a stack, like to build it up into a nice production ready looking ish thing. It's really not even all the pieces. There are a ton of these Lego pieces that I decided to plug together, and they may not be your favorite Lego pieces or favorite colors, but they may give you at least an inspiration of how these things plug together, and hopefully how give you a good idea of how I plugged it together. And you can see the exact source code for my cluster setup. That's available on GitHub at the link at the bottom there. You can find me on PyCat with a Z at the end on GitHub. And then there's even a full interactive tutorial to walk you through all of these steps. So you can open up in Google Cloud Shell, and it'll walk you through this Katacoda-like environment in your Google Cloud Shell to set up the cluster. And it kind of walks you through this where you use the module, which this is available as on the left there, to build out the cluster that's on the right. So the Lego pieces together kind of codified in Terraform, and then the picture on the box, if you will, the actual like diagram that I built out there. And you can tune these things as well inside the module to, let's say, limit the number of servers. Let's say you only want to start with one. You can change the number of clients and scale those out. And the only real required variable here is the Google Cloud project you want to deploy this in, and as well as the actual having the application credentials to be able to talk to the cloud provider. And to get an idea of that like full workflow, I use a HashiCorp Packer to build out the images that's going to be deployed by this Terraform module, and then Terraform init to pull in any of the required providers, any of their third-party code, and then actually Terraform plan and then Terraform apply to get the cluster. And then we can start thinking about the Nomad cluster in this sort of mindset, or how at least I think about it, is this compute kind of cluster, obviously, and it's made up of these clients. But I don't really think about the clients, at least not too much. I really think about these things in job files, and that they're deployed somewhere in the cluster that's available. And I can target specific clients if I wanted to, or specific attributes about a client. But just getting started, this is just kind of all these clients are just effectively running Docker, so I can schedule Docker containers on them, or at least that's how I configured mine. And so I can start thinking about these things as Nomad job files and then add groups inside of my job file. So in this case, a Grafana group that contains a single Nomad task that's going to run my dashboard, which is just that little Grafana container, and it's pulled in with the config here. Very, very similar if I wanted to deploy Prometheus. But the problem here is these are obviously just two kind of floating containers in my cluster, not connected in any meaningful way quite yet. But we can solve that with console. In this case, Nomad allows us to express these console connectivity configuration in the job file itself. So I can, in this case, specify the service as Prometheus, and it's available on port 9090, the default port. And so that'll be available as a way for me to connect to that service running in this container through that connect sidecar proxy. And then on the Grafana side, I also need that proxy for these things to connect. And in this case, I also am going to do this little proxy upstream so I can connect on localhost 9090 in the Grafana container, which is going to go through the proxy and then to the Prometheus instance. And this gives me that big advantage using Console Connect inside of Nomad, where it has a really good integration to be able to enable the service connectivity, which makes actual configuration also really nice under the hood, which I'm going to show in a second. But these now two things can connect, and they're literally just using localhost as you might do in development if you're running this on your laptop, if you will. And then I want to be able to connect to this, but outside of the service mesh that I started building out between these Grafana and Prometheus instance, I also need a way to be able to connect to it from outside the mesh. And in this case, I could use a static port. And this is just going to define a static port available on a client wherever this container was scheduled. And I'll be able to talk to it on port 3000, and that'll map to port 3000 within the Grafana container. And this opens up some really interesting sort of patterns where if I want to now enable some ingress type features, I have that port 3000 that's available as a client that's somehow routable. So if I had the cloud provider that has a native load balancer, I can target Nomad client instances, and I can have a health check just on any ones that, let's say, have port 3000, which could enable routing to my Grafana instance. This opens up more than just that, where I have a load balancer with a console integration, could be running inside a Nomad, could not be, depending on what you want. Or you could have a load balancer managed by console NIA, which is a feature of console to be able to use console Terraform sync to be able to drive the configuration inside of, and let's say an external load balancer here. And just like so many different things, like these things can piece together in so many different ways. I have this port, I can connect to a boundary or SSH or like what have you. There's so many options here. And taking a step back to understand like what exactly I deployed inside of the cluster to start enabling this Grafana and Prometheus workflow. I have a user on the left here, and they want to be able to talk to Grafana, and that's what that Nomad static port is going to enable in some fashion, a load balancer, SSH, etc. And then Grafana is talking to Prometheus, and that's using Console Connect. And Prometheus can be configured to use console as actual a service discovery mechanism. So the way Prometheus works is that it can be configured in a YAML file. We can specify a console service discovery server that it can then be used to discover specific services out of that console catalog, where all the services that we had in the service stanzas before could live, or as we add them to our cluster, can be attached to. Now, any of those Prometheus endpoints, metrics endpoints that are discovered, either inside the cluster or through console, doesn't necessarily matter, but the real kind of key feature is that Prometheus is scraping metrics endpoints here, and we can be able to then visualize that in Grafana as the user. So we modeled the Nomad job together to get this Prometheus and Grafana thing actually deployed, or to actually deploy it, we need now run Nomad run to actually run the job. And then to connect to it is just one example of how we can do this. I'm using SSH port forwarding to be able to connect to port 3000 on my local host on my laptop, and that's mapped to port 3000 on that client. In this case, it's client 2 that I was scheduled to. And then it's really nice workflow. If I was talking about before, it's a really nice configuration workflow. If I open up localhost 3000 on my laptop here to get started, this is the exact getting started sort of workflow that I have if I was just getting started with Grafana on my laptop. I log in, admin, change the credentials, get that sorted. And then the only Prometheus configuration that's required now, because it's connected and it's available on localhost 9090 in that Grafana container that's now able to connect through console. I just have to put localhost 9090, and that's the exact configuration that I would get when I was getting started insecurely. And now securely, I get this exact same workflow, which I just absolutely love. And the only way you have to make sure when you have console deployed in a secure fashion, we have these default deny policy. And so we want to explicitly allow these services to talk. The Grafana instance that we registered in the Nomad job and the Prometheus instance that we registered, we want to allow this one-way communication from Grafana to Prometheus. And we can also codify this in Terraform to do a console configuration entry to allow this communication, or through the wonderful UI as well. And we can continue to codify things. The Prometheus configuration, let's say we built out a Prometheus dashboard, we can export that model, and then we can codify this with Terraform. So we can start getting more configuration as code here. And now that we have the Nomad cluster, we got some observability tools here with Prometheus and Grafana and the service discovery using console and the way to connect these things. Now we can kind of talk about observability and monitoring some fuzzing workloads that we're going to run in Nomad here. And when I'm talking about observability, and observability has like plenty to talk about. Right now I'm just talking about just like being able to observe a value over time, monitoring the thing. And I probably want to be able to compare, multiple things. In this case, there's 2 lines, and I'm observing 2 values from 2 separate things over time. And this is just what I'm trying to get at. I want to be able to visualize some values in this way, a time series type way, right? And if I go back to GoFuzz and remember what's required for me to get started with, or to start using GoFuzz, I just have this log output to standard error, and I don't have a way to do it so nicely. At first, I started doing GNU plot. Then I started thinking that I need a bit of a higher level. And so my solution to that was to make a custom Prometheus exporter. And so I have a GoFuzz exporter that can slurp up those log lines from the GoFuzz. We can see at the usage at the bottom right there. And then slurp that up and then transform that into a Prometheus endpoint to be scraped. And so we can then start plugging these together in some interesting ways here and be able to monitor the output of our GoFuzz log, or of the GoFuzz logging here, but using Prometheus and Grafana. So the actual source code, it's available. And this is really the guts of it, right? Like for each line I get, I try to parse the line. I even try to keep track of the lines that I couldn't parse in case there's something weird. And then I keep track of all the workers, the corpus, etc. And then I even print out the lines back to standard error, so you still see them if you were using Nomad logs, for example, or you're using some other log forwarder. But now we have all these pieces. We can really get into fuzzing Nomad with Nomad. And like this is like, I was always so giddy. I love this, but the workflow, right? Then it's like, okay, I need to identify a fuzzable function in Nomad, and then build a container with our harness and then our custom Prometheus exporter here. And then we'll submit a job, Nomad registered as a console service, and then we're going to start monitoring that job with a Grafana and then triage the results. So just cloning Nomad here. I'm using ripgrep just to look for some sort of interesting function. Parse is a really good string to start with when you're looking for fuzzable or useful fuzzable functions. We can get much fancier here, but just as a really good getting started, ripgrep is totally fine, or regular grep if you like. And then build out our fuzzing harness case in a Go file. We're going to build out the actual harness. It's that fuzz function, a Docker file, build it out, and then we're going to need to probably export that Docker container somewhere. Google Cloud Storage, a container registry, what have you. So here's an example of actually like fuzzing Nomad with Nomad. Here's like an example. Here's an example, a very simple example harness to get started with. We have that very similar build tag at the top that we have with the PNG package from before, and we imported just in this case the HashiCorp Nomad ACL package, because we're going to parse the ACL parse function, and we can transform the slice of bytes to a string built in Go. And then we can return some stuff, and hopefully we get our returns correct. And then build that container out. So the rough steps are here. And I kind of abstracted a little bit away just to fit it on a slide with a make build, but just running Docker build command. And then start sh can be kind of helpful for wrapping up the commands that are going to run when the container starts. In this case, it's going to run go-fuzz build and then pipe it to the go-fuzz exporter that we saw before and then the README. And so a full Nomad job to start running this fuzzing workload, just this single group here. We're going to have a group that has a network stanza, a service stanza, and a task stanza. We're going to break down the service and tasks just because those are the larger ones. But the important one kind of though is the network, and we're going to declare a port. In this case, it's not a static one. It's going to be a dynamically allocated port on the client, and we're going to be able to map that in a different way here in just a second. So let's look at how that looks in the service block. So we have a service called fuzz, and we're going to have to update our Prometheus instance in a second to be able to find these things. And then we're going to have a port, and that's called fuzz from the port stanza and the port allocation of the network stanza. And then in this case, we have this connect sidecar service that's going to do something really neat, where we're going to expose a specific path, the metrics path that's from the go-fuzz exporter, and it's protocol HTTP, and we have listener port fuzz. And so that dynamically allocated port, which is going to be registered inside of console, is going to be able to be discoverable by the Prometheus instance. And this is going to be able to this is going to allow us to be able to talk to this metrics endpoint outside of the actual console service mesh, but we're limiting the exposure using this path here. And then we're going to be able to map that to the local port 4022, which is the port that the go-fuzz exporter listens on by default. And so the task that's required is we have a Docker driver. In this case, I have a container being pulled from Google Cloud Storage, and then we're going to mount. We're going to have to use a mount as a tempfs to give us this nice memory-backed file system to be able to basically just read and write to disk backed by memory in a much faster way without even having to thrash SSDs or even like think about that kind of nonsense. And then we just allocate 4 gigabytes, which is a pretty sizable chunk, though we can obviously grow that and shrink that as needed. So that's that whole group that's required to run this fuzzing workload. The Prometheus configuration, as I was alluding to before, and there's the console service discovery config, which takes up most of this, but just looking at the bottom there, the services, and we have fuzz, and that was the name of the fuzzing workload that we registered inside of the Nomad job. And so Prometheus is going to be able to automatically pick those up as they start inside of Nomad, and we're going to be able to start building up these dashboards. We're going to be able to monitor the workers, the executions per second, the coverage, the corpus size, and all the things that were from the go-fuzz log output inside of our Grafana dashboard here from the Prometheus metrics endpoint. And as I'm getting on time here, just some like really quick things. I can do really wonderful kind of experiments here. So in this case, I'm curious if it's a CPU intensive workload, what if I pin stuff to a specific CPU? I can use the lscpu command to check how many number of CPUs are available if I was just like on the client. And then I can, in the job file, start doing some configurations, actually specifying the amount of resources I want to allocate for this Nomad job, setting a hard limit if true. In this case, only allocating this fuzzing job to a single CPU. And then we can do those really interesting experiments where you can do like an uncapped multi-core fuzzer versus a single core capped fuzzer and get an idea of like, what's the advantage or disadvantage potentially? And here's like an example over time, and I probably won't have time to like read the tea leaves here with you, but we have more executions per second, right, from the multi-core one, which makes sense. But one of the really interesting bits here that I want to focus on, we can see the workers at the bottom right to get an idea of the orange maps to the multi-core and the green maps to the single core. But the coverage is the really interesting bit here to me. They effectively start converging at the exact same coverage. You give it more executions per second, but you start really you get a diminishing return. And it might depend on the scale of whatever the fuzzing architecture or the actual fuzzing harness that you build. And that's where like kind of the art kind of comes in, figuring out how do I analyze this very almost black box type experience here. But and that's not the only way you can monitor these things. Nomad has a wonderful topology view, which you can get just like this wonderful view of like the fuzzing workloads and how much you allocated. So you can see the big fuzzing workload on client 1 where I gave it all the CPU, so I gave it all the CPU capacity and just a low, the 4 gigs of memory, and then the smaller one there, and client 0 that's living alongside of the Grafana or Prometheus, whatever other task that's running there. And some other random notes in just like the last minute here. GoFuzz has a really cool way to actually do distributed fuzzing. And so we can map this in a really interesting way. Because I'm limited on time, I have to go through this a little fast. But GoFuzz coordinator, I specify as localhost 4023. And this is going to start an endpoint that is going to be able to accept workers. And I can start a worker by doing this. And this is very similar to how I normally run GoFuzz, but in this case, I'm providing a worker flag, which is the coordinator address, weirdly, but that's what it is. And then this actually doesn't have any output. And so the output only exists in the coordinator. And so I only really need to slurp up the logs and run the exporter on the coordinator, interestingly. We can kind of see in the worker, if I only gave it one, you'll get one worker in corpus. And then this is like the really like interesting thing to me. Now I have like the console, and I can run it in Nomad, and I can do like for a single fuzzing workload, I can use those exact same concepts that I use to connect Prometheus and Grafana to build out this distributed fuzzing using a coordinator job, a worker job, and then they're connected using console connect, which is just wonderful. And the only real like network configuration I have to worry about is the console service intention. So here's the service config for a coordinator. I'm not going to go through the entire job. Thankfully, I didn't do that because I'm already running low on time. And then here's the service, the actual like service fuzz. This is going to be a thing that's going to be scrapable by Prometheus. Then here's the only thing that's required for the worker. You can kind of see that resemblance to the 9090 Prometheus thing from before. In this case, local bind to 4023. Do a service entry config so these can talk. And then we can start monitoring these and then do some really interesting stuff where we're running the multi-core and the single core and then the distributed fuzzer, start adding more resources to these, start finding bugs in GoFuzz at the bottom there. I don't have time, but that's a bug in GoFuzz. That's so neat. And then you can scale this up manually in Nomad as much as you need. So if you need more CPU capacity or you need less, whatever you have, you can always use the Terraform module code to be able to manually scale up the cluster. And thank you very much. Hash Talks is great. This is so wonderful to be able to talk, thank you.
You are fine. Let it never be said that you are not excited about what you do.
Very excited.
There is a question in the chat. I know you're going to end up over there anyway, but just to give it some promotion, somebody wanted to know where they could read on GoFuzz.
Yeah, the GoFuzz, if you go on GitHub, look at GoFuzz. I forget how to pronounce the name, but effectively, you can go read the documentation. And I think the best kind of documentation for GoFuzz is the source code. Not the best, but that is what it is. And things are going to change over time. If you remember the GoFuzz design, the first class fuzzing design draft, and that's going to change some things, and it's going to have its own implementation details. So reading the source code for both of those, quite honestly.
Awesome. Thank you so much.
Thank you.
Viewers, he will be headed to chat, so feel free to just throw all the questions you have at him. Awesome. Thank you, Kat.